Hello there, welcome to Unit 3, and that's Atomic Theory. And with the first session, we'll be doing history and development of the atomic theory. Let's look at the objectives. The first objective for this section is to understand that the modern model of the atom has evolved over a long period of time through the work of many scientists. And secondly, state and explain Dalton's atomic theory. All matter is made up of atoms. This is something we now take as a given, and one of the things you learn right back at the beginning of high school in chemistry or physics class. Despite this, our idea about what an atom is surprisingly recent. As little as 100 years ago, scientists were still debating what exactly an atom looks like. This graphic takes a look at the key model proposed for the atom and how they change over time. It was a long wait before these foundations were built upon. It's until the 1808 that the English chemist John Dalton started to develop a more scientific definition of what an atom is. He drew on the ideas of the ancient Greek in describing atom as small, hard spheres that are invisible, and that atoms of a given element are identical to each other. The latter point is one that pretty much still holds true, with the notable exception being isotopes of different elements, which differ in their numbers of neutrons. However, since neutrons wouldn't be discovered until 1934-32, we can probably forgive Dalton's this oversight. He also came up with theories about how atoms combine to make compounds and also came up with the first set of chemical symbols of some known elements. Another breakthrough came in the late 1800s when an English physicist, J.J. Thomson, that's Joseph John Thomson, discovered that atom wasn't as invisible as previously claimed by Dalton. He carried out experiments using the cathode rays produced in a discharge tube and found that the rays were was attracted by a positively charged metal plate, but repelled by negatively charged ones. From this, he deduced the rays must be negatively charged. By measuring the charge on the particles, in the rays, he was able to deduce that they were 2,000 times lighter than hydrogen. And by changing the metal, the cathode was made from the could tell that these particles were present in many types of atoms. He had discovered that electrons and shown that atoms were not invisible, as proclaimed by Dalton, but had small constituent parts. This discovery won him a Nobel Prize in 1906. Fast forward in 1904, he put forward his model of atoms based on his findings as the Plum-Paulding model. Scientists have started to peer into the atoms, but Thomson's model would not hang around for long, and it was one of his students that provided the evidence to consign to the history. So, which came in the Ernest Rutherford, who was a physicist from New Zealand, who studied at Cambridge University under J.J. Thomson. It was his later work at the University of Manchester, which would provide further insight into the inside of the atom. This work came after he had already received a Nobel Prize, right after the 2 years of J.J. Thomson receiving his, that is 1908, for his investigation into the chemistry of radioactive substances. Rutherford devised an experiment to probe atomic structure, which involved finding positive charged alpha particles at thin sheets of gold foil. The alpha particles were so small they could pass through the gold foil, and according to Thomson model, which shown the positively charged fused over the entire atom, they could do so with little or no deflection. By carrying out this experiment, he hoped to be able to confirm Thomson's model, but he ended up doing exactly the opposite. During the experiment, most of the alpha particles did not pass through the foil with little or no deflection. However, a very small number of particles were deflected from the original path at very large angles. This completely unexpected, as Rutherford himself observed. It was almost as incredible as if fired a 15-inch shell at a piece of tissue paper and came back and hit you. The only possible explanation was that the positively charged was not spread throughout the atom as J.J. Thomson proposed, but concentrated in a small condensed center, and that brings about what? The nucleus. Most of the rest of the atom was simply empty space. Rutherford's discovery of nucleus meant the atomic model needed a rethink. He proposed a model which the electron orbits the positively charged nucleus, while it was an improvement of what? J.J. Thomson's model. He didn't explain what kept the electron orbit instead of simply just firing into the nucleus. Then came in Bohr, Niels Bohr. Bohr was a Dutch physicist who set almost trying to solve the problems of Rutherford's model. He realized that classical physics could not probably explain what was going on in the atom level. Instead, he invoked quantum theory to explain the arrangement of electrons. His model postulated the existence of energy levels or shell of electrons. Electrons could only be found in these specific energy levels. In other words, their energy was quantized and couldn't take just any value. Electrons could move around these energy levels, but had to do so by either absorbing or emitting energy. Bohr suggested a suggestion of stable energy levels addressed the problem of electrons that was spiraling into the nucleus to an extent, but not entirely. The exact reasons are little more complex than we are going to discuss here, because we are getting into complex world of quantum mechanics, and Bohr himself said, if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. In other words, it gets kind of weird. So let's talk about Schrödinger, who you've probably heard of one way or the other. So in 1926, Schrödinger proposed that rather than the electrons moving in fixed orbits or shells, the electrons behave as waves. This seems to be a little weird, right? But you probably already recall the light can behave as both what? A wave and a particle. And it turns out electrons can too. Schrödinger solved a series of mathematical equations to come up with a model for the distribution of electrons in an atom. His model shows the nucleus surrounded by cloud of electrons density. These clouds are clouds of probability, right? though we don't know exactly where the electrons are, and we know they are likely to found in a given region of a space. These regions of space are referred to as electrons orbits. This is perhaps understandable why in high school physics or chemistry lessons don't lead us to straight with this model, though it is an acceptable model today because it takes a little more time to get into your head around. Now let's look at Dalton's uh, atomic theories. So Dalton developed the first official atomic theory. From his results, he developed the following 5 principles of the atomic theory. And this one, you have to know it offhand. And the first point is all matter is made up of indestructible atoms. Secondly, atoms of the same element are identical in their physical and chemical properties. Atoms of different elements have different physical and chemical properties. Atoms of different elements combined in simple whole number ratio to form chemical compounds. In chemical reactions, atoms cannot be subdivided, created, or destroyed, but rather they are combined, separated, or rearranged. Which of his principle remains true today? I'll give it to you so that you give a very good thought about it.